Welcome back to the Cloud Flight Simulator series. My name is Eric Johnson. This is part 4, least privileged pods with Kubernetes workload identity. So over the course of the simulator series so far, I kicked us off very early on in January, going through what the Cloud Flight Simulator series was going to be about. I introduced you to our simulator, which is a new browser-based way to access a bunch of the different tools such as GitLab and the OpenVS Code server and things like that we've got running inside of our cloud environment here at SANS. And then we talked about GitLab and we talked about some things with Vault and OpenID Connect integrations. And a lot of that information in part 1 is going to come back into the session today as we talk about workload identity inside of Kubernetes clusters. In part 2, Ben Allen gave us a nice look at how we can use Kubernetes and admission controllers and policy guardrails to protect our clusters. And that's another piece that I'll probably gloss over today is just what is Kubernetes and how are we operating it. We're going to focus on some workloads that are running inside of it pretty quick here. In part 3, John Ziola walked through the supply chain and how we can actually get attestations for what's inside of our container images and how to produce signatures on those attestations. All things that would lead to the point of actually having a pod running. So if you haven't seen the first 3 parts of the series, I would highly recommend circle back. You can go register for those, and I believe they will eventually, if they're not already, be on our SANS Cloud Security YouTube channel. So you can get yourself up to speed with what we've covered thus far. Before I jump in, very quickly, I'll do an introduction. My name is Eric Johnson. I'm one of the authors for SEC 540 and SEC 510 and SEC 549 inside the SANS Cloud Security curriculum. I work at Puma Security, where I focus a lot on cloud infrastructure, architecture, CI/CD orchestration, and deploying workloads out into cloud environments. My contact info is on the slide. You can find me on LinkedIn. You can also find my full bio out on the SANS website as well. So in the interest of time, I'm going to just jump right in because I have 5 demos I'd like to get through today throughout our session. So every minute matters as we lead up to the top of the hour here. So let's go ahead and take a look at our agenda real quick. The first thing I want you to know is that we're going to be working inside of managed Kubernetes services inside of AWS and Azure for the various topics that we will discuss during the section. As we take a look at workload identity, what does that actually mean? It means you've got a pod that is running inside of your Kubernetes cluster. And that cluster itself might have different pods with different responsibilities that require different permission sets. So the question is how can we assign an identity to those workloads and then give them a least privilege policy so pod 1 can't access data that's supposed to only be able to be accessed by pod 2. That's what we mean by workload identity. We'll take a look at a couple of anti-patterns, which is giving pods long-lived credentials or putting permissions up at the node level and letting each of the pods inherit those permissions. We'll see what that looks like. And then we'll go through 3 different workload identity configuration options. One of them inside of Azure, which is based on OpenID Connect, and then 2 inside of AWS. One is based on OpenID Connect, and the second one inside of AWS is relatively new, and it is an EKS feature only called pod identity. So as we take a look at the different services, I mentioned the Elastic Kubernetes Service in Amazon, the Azure Kubernetes Service in AKS, and then there's also GKE, which is probably the most advanced and you could argue one of the most commonly used Kubernetes services inside of Google Cloud, as they're the owners and creators of Kubernetes themselves. Unfortunately, we don't have time to really cover the GKE story here in this session, but perhaps down the road, let me know if that's something that would be of interest to you. We can do a dedicated session for GKE and compare how GKE does workload identity to how AWS and how Azure implemented it. So drop me a line if that seems interesting, and maybe we can take a look at adding that into a discussion at a later point in time. So let's jump in and take a look at the pod identity workflow and some of the options that we've got. As you take a look here, so at the top, very top of this diagram, and let me zoom in on this a little bit so you can see it. So we've got a worker node, and the worker node itself has a namespace in it called DM, which for those of you that have seen a lot of the demo environments that I've set up in the past, DM stands for Dunder Mifflin. So a lot of the lab environments are based on the fictional company Dunder Mifflin, which is from the TV show The Office. So we've got some workloads that are powering maybe the Scranton branch here. And then one of them is this little web app. And this web pod is running inside of the Dunder Mifflin namespace. That web app needs permissions to talk to some resources inside of Azure, for example. And the idea here is that some sort of secret or some sort of token is going to need to be issued to that web pod. And then using that token, we can authenticate into an Azure tenant or an Entra ID tenant. And that'll give us access to some storage data and some key vault secrets that that web pod needs to go in and do its job. So the idea here is we're giving it a credential to access information in the cloud. The question is, well, what kind of credential is it? And what do the different cloud providers support for doing this? So option one, which is an anti-pattern we'll look at first relatively quickly, is using long-lived credentials. So this would be an Azure client ID and a client secret that allows you to authenticate to the Azure stack. Now, on the AWS side, that can easily be access keys for an IAM user that's got permissions to those resources. On the Google side, it could be a service account key file that lets you access Google Cloud resources. So those would be stored somewhere inside the pod. Getting rid of those, if we decided that's a terrible idea, which I'll tell you why here in a moment, we could use the permission inheritance model from the worker node itself. All of the managed Kubernetes services support assigning an identity to the node, which is the actual virtual machine that's running all of these pods. That service account can have permissions to those resources, but there's some problems we'll take a look at with that model. And then we'll get into the workload identity and the pod identity mechanisms in AKS and EKS to see how we can access these resources. So let's take a look at anti-pattern number one, which is long-lived credentials. So that's our first topic of discussion. Now, I've done a lot of work with identity and killing off long-lived credentials over the course of the last year or so. And I'll give you the short story here. I've got other talks and webcasts out there that talk about why these long-lived credentials are such a terrible idea. The problem really is that they typically live forever, right? They're credentials being generated for a machine identity. And if you deactivate them or rotate them, then usually the workload breaks. And you would have to go in and reissue those credentials to the workload or read them in dynamically from some location. And that's very challenging to manage for us. So the overhead here is fairly challenging to deal with as far as just rotating them goes, which means they kind of live in infamy. And then you've got the attacker path, which is if you can find them, you can compromise whatever cloud provider environment they've got access to. Now, common locations, as you look at a workload that's running, are covered by the MITRE ATT&CK technique 1522 unsecured credentials. And if you get into one of these pods, if you're on the shell, so let's say that you've got an application security flaw or some sort of remote code execution vulnerability in a library, you typically might look in a configuration file inside of that container. You might reverse engineer the source code and find it inside of a binary. You might find it in a Kubernetes secret that's been bind mounted into a volume. You might also find them in environment variables just by running the env command. So those are the sorts of techniques covered in the unsecured credentials item inside of the MITRE ATT&CK framework. And it's something that's very commonly found to be the entry point or the cause of a breach in the cloud. So common places that you'd look, I mentioned proc self environment or just by running env, //.aws, //.azure, //.config.g/gcloud. Those are different locations you can find these tokens or these credentials, and then you can just extract them from the pod, and you can use them from your attacker-controlled machine. So in our first demo, what I wanted to show you is what that might look like. So let me switch over to Firefox. I've got a browser here. This is the SANS Cloud Security Flight Simulator. I've used it to spin up a Kubernetes cluster and in AWS and in Azure. And right now you are looking at a Kubernetes manifest file for a pod that I have called Evil, and it's in a namespace called Sabre. So I've got two namespaces, one for Dunder Mifflin DM, the other one for Sabre. And the idea here is I spun up an Azure pod and AKS that was pre-populated with really just the Azure CLI base image, so I can run some AZ commands. And then if you look at the environment variables, this is an example of where you might find those credentials. So we've got the client ID, client secret, and the tenant ID here. And what I want to do is see how you could steal those and use them. So if I run K, which is aliased in my bash for kube control, so I'll just run the first command as kube control, so you understand that that's what K means, right? It's the same thing. And then in the context, I want to look in the AZ cluster. I'm going to do a git pods in the Sabre namespace. And you can see that in the Sabre, I've got this evil pod running here. So that evil pod is where those environment variables are. And you can easily see them if you describe that pod. So now I've described the pod, and I'll scroll up on this a little bit. So if you've got access to the kube control or the Kubernetes API server, we can very easily see that just sitting here in the environment variables are those long-lived secrets that we really do not want to give to anybody. So if you just pause there and think about what that means for a moment, that means that these secrets are in the env in the container, which we'll look at in a moment, but they're also stored in the Kubernetes cluster themselves inside of the actual cluster. So on the control plane inside of etcd, you've got these things stored, and anybody with access to the API server can potentially use these. So that's location number one. On the other side of it, I'm going to now run a kube control exec command, which I've got as a shortcut here. So I just ran kube control exec into that evil container image. And from here, you can see that I'm inside the container. And if I run env and grep out the Azure environment variables, you can see that these three environment variables are sitting there in the env as well. So as you take a look at what this can do, all you really need to do, if you're an attacker and you steal these, you can run an AZ login command, service principal, and you can log in with the client ID, client secret, and that Azure tenant ID. So we're just going to use these to sign into the cluster or sign into the Azure tenant. And you can see that I'm now authenticated into a subscription that I own. And with that, I can easily run an AZ account get access token. And if you run that, what you'll notice is that we've now got an actual JSON web token that has been issued to that particular service principal for accessing one of the management control plane APIs inside of Azure. And that's really the problem with long-lived credentials. As long as those are active, which usually they live for years and years and years, we can easily steal them and use them from wherever we want. Now, just taking a look inside of that token. So I'm going to set up a little variable called JWT here. And now I'm going to do a JWT decode, which is a shortcut. And I'm happy to send you that as shortcut as well if you want to take a look at what this is doing. But it's really just grabbing the JSON web token payload, which is the second parameter of that. And it's decoding the body of it, which is base64 decoding it. And you can see here that that token was issued by my Active Directory tenant. And you can also see on the subject side that this is the client ID inside of Active Directory. So this is a valid token that's been issued by Azure for accessing some of those Azure resources. So recapping here, what we did is we took a look at the pod definition, and we also took a look inside of the container itself that comes to life. We stole some credentials. We can now pivot and use those against Azure. So demo one, the big takeaway there is we need to kill the long-lived credentials off. We should not use those. How can we do it? Let's start the conversation of getting rid of long-lived credentials in favor of short-lived temporary access keys that we can use for a few minutes and then they die and go away, which can limit the blast radius of one of those stolen credentials. All right, so anti-pattern number 2. Now this is getting rid of long-lived credentials. Kubernetes node permissions are inherited by the pods, and you can access those temporary credentials from the node's instance metadata service. So that gives you a way to talk to the cloud provider APIs without using long-lived credentials, but there's an issue there. So let's take a look at how it works first. So the idea here is that instead of using env or dumping long-lived credentials into the worker or the pod itself, we can leverage the permissions assigned to the worker node up here at the top level. So you would create your Kubernetes cluster for every node. The configuration will essentially ask you, what permissions does this node need? Now, in the normal scenario, we can send out the permissions that you would usually need to create a network interface in the VPC, for example, because as you spin up pods and you create load balancer or ingress services, it's probably going to need to create a network interface with a private IP in that VPC. That's a permission that would normally be given to the node so it can manage resources in the cluster for you. So you'll go through all of these default permission sets that are needed for the node to operate. But then you might tack on a couple of extra permissions that say, oh yeah, and you can read from this S3 bucket, and you can read from this secrets manager resource. So the node can do that. Now, when the web pod comes to life, it can reach out to the node's instance metadata service in the cloud. It can get those temporary commands and get access keys that give it permissions to read from those resources. So that's the normal use case here. And it is something that basically happens by default inside of these managed Kubernetes offerings. The problem is when you have multiple pods running on the node. So if the web pod is supposed to have access to S3 and secrets, but me over in my Sabre namespace, I just spin up kind of a naked evil pod, which means no credentials inside of it or anything like that, no service account attached to that pod or anything. I'm just going to essentially spin up this pod, and it also inherits the same IMDS access that the web pod has, which means the evil pod, just by it being deployed, has access to the same S3 and the same secrets manager resources that the web pod does. Hopefully we're seeing the problem now. Every single pod running on this node will inherit those worker node permissions, which can be problematic. So demo number 2, let's go over to EKS. I'll show you what the pod permission inheritance model looks like. We'll inspect the Sabre evil pod that's running on my AWS cluster, and we'll see that we can go in and look at that instance metadata service data, and we're already authenticated as the role. So switching back over, I'm going to switch my terminal over to the AWS cluster, and we'll take a look at this evil deployment manifest. So here's my evil pod going to the Sabre namespace. And if you take a look at the container definition, it's much smaller than what that Azure one was. We're deploying the AWS CLI base image, and you'll notice that as far as the environment variables go, there's no credentials there, right? We're not giving it long-lived credentials, which is better than what we had before, but that means we're going to default into the node's credentials. So let's take a quick look at our pods that are running in the Sabre namespace over in AWS. So on the AWS cluster, I'm going to run git pods -n Sabre, which means show me all the pods running in the Sabre namespace. There's the evil one. We've also got a web one, which I'll look at here a little bit later. For now, we're just going to play around in the evil pods. So you can validate if I grab the metadata for the evil pod, and you kind of take a look at the different environment variables. Again, no long-lived credentials here, so that's an improvement. But if we go ahead and exec into that pod, so let me go ahead and do a DM Kate's exec evil. So this is going to run kube control exec into my pod. I can see here, if I run AWS STS get caller identity, we'll let that come back. We'll see that magically the command line interface is automatically being authenticated. And if you look at the role here, it's using an assumed role, which is called DM EKS node role, and then this random ID, which is just unique to the deployment that I've got out here. So what that tells you is that there are credentials inside of this pod already. And if you take a look at the name of this role, you'll notice it ends with I-random identifier, which is an instance ID. That right there tips you off that you are being authenticated as the role that's assigned to the EC2 instance that the pod is running on. So we basically reached out to the instance metadata service and we have grabbed those temporary credentials. Now, under the hood, if you're not familiar with that instance metadata service, I'll run a curl command real quick and I'll just show you what that looks like. So what the CLI did when I ran STS get caller identity is it reached out to 169.254, 169.254 latest metadata IAM security credentials. And if we look at the output of that, it basically just says, well, what security credentials are available for this EC2 instance? And you can see, well, there's the name of that role. And then if we run another curl command with the / role name on the end, so there's the next part, we can run that command and you can see the response gives us an access key, a secret access key, and a token that can all three in those combinations be used to communicate with the AWS APIs. So now the permission sets that have been given to the node are very apparently available inside of the pod itself. And that can be bad because if there's permissions for the web pod and DM, the evil pod now has those same permissions and I can pivot into S3 or I can pivot down into the secrets manager, whatever it is. So node permissions are better than long-lived credentials. However, they're still an anti-pattern because it becomes very difficult to perform least privilege inside of a Kubernetes cluster if you've got multiple pods with multiple responsibilities running inside of that cluster. Which brings us to the workload identity part of the conversation. What we would like to do is use OpenID Connect to actually assign permissions on a pod by pod by pod basis. And that's what workload identity allows us to do. So this is the longer part of the session here where I'm going to go through a few slides at least to describe how this is all set up. The first thing that you need to understand when you're looking at workload identity and pod permissions inside of a Kubernetes cluster is a service account. So a service account is not the same as a Google Cloud service account or a service principal in Azure. These are Kubernetes specific resources. So every Kubernetes namespace will have a default service account created inside of it. And then you can create additional service accounts that are also inside of a given namespace. So in order to set up workload identity, what we're going to do is create a service account called web. And that web service account can exist inside of the DM, the Dunder Mifflin namespace. And then you can assign permissions to the cluster. These are for performing operations against the cluster through the Kubernetes API server using roles or a cluster role. And what you would do is if you needed your pod to be able to communicate with the Kubernetes API server and maybe read a secret or read a container image from a registry, you can give the service account a list of secrets or image pull secrets resources that it has access to. And if you want to create custom roles with access to the API server, you can also create a role inside of a namespace, or a cluster role as a cluster-wide role set of permissions. And then you can use role bindings to essentially grant that service account permissions to those roles or cluster roles. So those are going to give it access to things inside of the Kubernetes cluster. In order to create a service account, you're going to have to update your configuration a little bit. So what I'll do is go into my web deployment.yaml file, and I'm going to create a new service account resource. Notice the kind here on line 2 is a type of service account. And then we've got a namespace called DM. So we're going to say, I want to create a new service account in the DM namespace. And I would like to give it a name of web-sa. Now that could be anything you want. It could just be web. It could be Eric's awesome service account. You just have to know what the name is. And then you would apply that change, and the API server will create you a service account called web-sa in the DM namespace that you can then assign to our web pod. And to use the service account inside of your pod, you go update your web deployment, and you just need to add one line to it. So you're going to add a service account name, and notice you give it the name of web-sa, which matches the name up on line 4. So at this point, when you deploy that change, you have created a service account for your pod, and then you have assigned the service account to the web pod. And now you've got an identity for that pod itself. Now, the way that this works is when you go in and you deploy that, the Kubernetes server or the Kubernetes cluster is going to use its built-in embedded OpenID Connect provider to issue a JSON web token to that pod. So when that pod is created, it sees the assignment. I'm supposed to use the web-sa service account. It's going to go ahead and generate a JSON web token that is unique to that particular service account. And it's going to send that into the pod by mounting a volume to the pod when it's created. And the location of that token is going to be at /var run secrets Kubernetes IO /service account /token. So if you cat out that particular volume that's been mounted into the container, you are going to see that JSON web token sitting there. Now, if you decode that token, so we'd use that JWT decode command that I used to decode the first Azure token, you'd see a little bit different information inside of it. And Chad, I see your question out there. So yeah, I'll show you what that looks like here in a moment, and then I'll drop that into a gist or something that you all can poke around at. So if we decode this token that's unique for that service account, you'll see that the issuer is my cluster. So that's the unique issuer URL to a cluster that's running out in Azure's AKS. And then the audience is intended to be used inside of the cluster. So that audience is scoped basically to the same issuer. So this is how we can be using that token to authenticate to the APIs inside of the cluster. The subject is the big piece here. Notice the format for this. So it's a system : service account, and then : the namespace, and then the name of the service account itself. That's the unique service account that this token has been issued for. And you can use that to access the Kubernetes APIs. So understanding all of that, now you know how service accounts work. You also know how the Kubernetes OpenID Connect service provider is issuing tokens for in-cluster actions. We can start to take advantage of that setup that exists to use it to authenticate to the cloud provider APIs. Now, we don't have time in this webcast to go into the cloud provider's workload identity federation capabilities, but all you need to know for here is that all of these cloud providers support federation through OpenID Connect using an AWS identity provider, a Microsoft workload identity federation credential, or Google's workload identity federation. If this is new to you, this is going to be some prerequisite knowledge you need to start setting this up inside of Kubernetes specifically. I did an RSA session on this last year where I walked through cloud workload identity federation in AWS, Azure, and in Google. So if you go out to our GitHub repository at pumasecurity/Nymeria, you will find the GitHub repository that's got a link to that RSA presentation and the YouTube video, as well as a 2 to 3 hour workshop that I did with SANS last year. So if this is new to you, go do that workshop and listen to that YouTube session, and you'll understand how to set up all of these different cloud workload federation resources so we can consume the token that's being created by our Kubernetes cluster. With that prerequisite knowledge, it becomes very simple to start turning on workload identity to integrate your cluster with a given cloud provider. All you need to do is assign that service account and then make a couple of very small adjustments to the service account deployment.yaml configuration to tell your cluster, when you generate that JSON web token, I would also like you to generate another token with a slightly different audience that can be used to authenticate to the cloud provider itself. And the way that this works, and this gets into a topic that Ben covered during part 3 of the series, is that it uses admission controllers to set that up. So when I add a line, it's going to be an annotation to the deployment.yaml file that says, oh, I need Azure Workload Identity Federation to be enabled for this pod. It's going to send that request through a mutating admission controller, and it's going to look to see if that annotation exists. If the annotation exists, it's going to actually generate another JSON web token with the appropriate audience, and it's going to bind mount that into an additional volume for that container to use. And we'll see what this looks like here in a moment. So here's the change you need to add to the service account configuration. Azure's Kubernetes Service Workload Identity Federation has you add this annotation that says Azure Workload Identity / Client ID, and it has you set the Client ID UUID value. That's the same value that we saw in the first demo that was in an environment variable. And what this allows the mutating admission controller to do is inject a token that is allowed to be consumed by Azure, and it also tells it which client ID that token is supposed to be used for. So it maps the token to an actual principal inside of Entra ID for you. And then on the deployment, you add a label that says Azure Workload Identity / use. You set that bool to true. So that's all you have to do on the configuration side. Now, when you actually deploy that resource definition out there, the mutating admission controller is going to intercept that request, and it's going to inject a few things into the pod for you. So what you'll notice is that you've got a couple new environment variables, Azure Federated Token File, and that's an environment variable that the Azure command line interface and their software development kits, the code running inside of the pod, will look for. And if it finds one called Azure Federated Token File, and it says, here's where your new JWT is, it's going to be var run secrets, Azure tokens, Azure identity token. It knows to go grab that JWT, and it will use that JWT to authenticate into the Azure tenant instead of using that long-lived client secret value. So let's take a look at this configuration. So we're going to jump back over to the Azure Kubernetes cluster here, and we're going to look in the web namespace at our web pod here real quick. So we'll jump back over here. Let's get rid of this evil deployment YAML. If you look at the configuration that I deployed here, you'll notice those two changes are there. So here is your annotation for Azure Workload Identity Client ID, and we've set that to the appropriate client ID. And then here is the label on the actual deployment itself. So workload identity use equals true. So with all of that configured, we'll jump back over to our web pod in the DM namespace, and then we scroll up, and you can see here that we've got those volume mounts here. So there is the normal Kubernetes IO service account token that still is there. Just remember the audience itself is inside the cluster. And then you've got another one, var run secrets Azure tokens, that is going to give you the Azure identity token that you need. The environment variables now, notice we've got no long-lived client secret here. You've got a client ID, you've got a tenant ID, and you've got the path to the JSON web token. The three of those things combined will allow you to log into the Azure tenant the same way that we did before. So let's jump over and connect into that Azure pod now. So I'm going to exec into the web pod. And the first thing we can do is actually cat out the identity token. So we're going to go ahead and dump out the contents of /var run secrets, Azure tokens, Azure identity token, and we can see that that JSON web token is there. So let's go ahead and decode this now. So here, we're going to go ahead and exit the pod. I've copied that onto my clipboard. I'm going to say JWT equals the value, and we can JWT decode that JSON web token. So as we take a look at the differences in this token compared to the default service account token, the major change here, notice the issuer is still the same. That's still going to be issued by your cluster, but the big difference here is the audience. That is not your cluster anymore. It's the default used by Azure's Identity Federation service. So notice the audience is API Azure AD token exchange. And then you can see that the subject is still the same. So we've got the system service account, DM, web SA. So as you take a look at all of that setup, this audience and the issuer and that subject simply need to be trusted by your Azure Entra ID tenant. So what you do is you go into the service principal, and we can take a quick look for that over in my Azure tenant here. I'll show you kind of what the Azure side of this looks like. So what you're ultimately doing is you go in and create an app registration, and I've got a ton of them in here. So bear with me while I kind of look for the one that I created this week here. So here's the 212 one. So let me open this up. So this is the service principal inside of Azure that's got permissions to that vault and that storage resource. If you go to the certificates and secrets, you'll notice that I've got a federated credential set up here for login. And this is allowing some external OpenID Connect provider to authenticate to the service principal. The name is very appropriately named. It's DM app AKS web SA. So that's the service account that we just took a look at. So if I open this up and we take a look at the configuration on it, you'll notice that we've got 3 key fields here that describe exactly who is allowed to log in with this token. Notice the issuer URL. So that is that random issuer. But go back to the service account or the JWT, notice that issuer is identical. So it trusts that issuer. And then the subject is system service account DM web SA. So notice the system service account DM web SA subject is in there. And if you scroll all the way down, you'll see there's that audience, that Azure AD token exchange. So those 3 values match, which means when I run an AZ login, and instead of a password, I pass in an actual federated token, it's going to look for tokens issued by that URL. And if the signature on the token is valid, it will say if the service account is this value and the API audience is that value, it's going to allow you to authenticate to the tenant. So at this point, we now are using tokens that have a very short expiration life. And you could run a diff on that timestamp and see that that's going to live for roughly an hour or so. And if for some reason, if I compromise this pod now, I can still log into the Azure tenant with that token, but I've only got an hour to do the damage that I need to do inside of that Azure subscription before it expires and goes away. So that's the Azure workload identity configuration setup. Relatively simple if you understand the glue between the Kubernetes OIDC setup and the Azure OIDC setup. So this requires a little bit of extra configuration, and now you've got a least privilege role assignment set up for a single pod running inside of the Azure cluster. Switching gears, let's take a look at what this looks like in EKS inside of Amazon's Kubernetes service. So as we take a look at your service accounts inside of EKS, there's actually 2 ways to do this now. The first one, the original name was IAM roles for service accounts, or IRSA. Now, the IRSA method is very, very similar to what I just showed you inside of Azure. You install the workload identity admission controller, and it's going to look at the resource definitions. And if it sees you're turning on workload identity for a given IAM role, it is going to issue an additional JSON web token that allows you to assume a role inside of that AWS account for accessing that data. So the configuration change is more simple, only one change needed here. We're going to say eks.amazonaws.com/role-arn. And what you're doing here is you're telling the cluster which role should be mapped to the Kubernetes service account, very similar to the client ID that we set up inside of Azure. So this is the only change you need to make. And when you make that change, you're going to see the admission controller inject a role ARN environment variable and a web identity token file. In the command line interface and the SDKs will use those environment variables to authenticate into the into the AWS account and assume the role that's in the environment variable. So that'll just automatically happen as long as those environment variables are there. So let's quickly look at this setup. So instead of working on the Azure terminal, let's switch it over to the AWS terminal, and I'll close this AWS manifest out. So this is the only change I've made here. Annotations, EKS, amazonaws.com/role-arn, and I'm passing the role-arn here into the cluster. So that admission controller, let me exit out of this pod here, will intercept that, and it will inject those two environment variables for us. So let's take a look at this pod here real quick. So we're going to look on the AWS cluster in the DM namespace at the web pod, and you can quickly see, if you look at the mounts, same setup. You've got your default service account token. You've also got the EKS service account token that's going to be specific to the AWS IAM role assumption. And you can see we've got those two environment variables. So you've got the role ARN and the web identity token file. So if we go ahead and exec into that pod, so let me go ahead and jump in there, and we can cat out that token again and take a look at how that is different from the default service account token. So we'll throw that onto the clipboard. So let me grab that, exit out of here, JWT equals. So, and then we're going to JWT decode the JWT environment variable, and we can see subject is exactly the same, system service account, DM web, :web-sa. And then you've got the same sort of issuer. That's my AWS EKS cluster. And then the audience is the big one that's been updated to sts.amazonaws.com. So this token can be used to authenticate to the AWS resources. So that's how you can set up federation for the web pod into an AWS account. Let's quickly jump over to the AWS account. I'll go into IAM and I'll show you what the client side configuration looks like a little bit. So we zoom in on this a little bit. Here is that Kubernetes cluster identity provider. So if we come in here, you can see that that is the provider URL. So we trust tokens from that provider URL if the audience is sts.amazonaws.com. So that's the first half of the setup. The second half of the setup is in the roles trust policy itself. So if I take a look at the web EKS pod role here, you can actually see it from right here. You can see that this particular role trusts that identity provider that we just looked at. If I open this up and I look at the trust relationship, you can see that we are going to allow principals to assume this role if the JSON web token is issued by our Kubernetes cluster, and the subject is system service account DM web-sa. So that's going to allow your Kubernetes pod to exchange the JSON web token for temporary access keys that assume this role's permissions, and you can use them for 60 minutes or so, and then that will kind of die and go away. So again, short-lived rotating credentials. All right. Last demo of the webcast. There's an additional capability now that came out a few months ago inside of Kubernetes called EKS Pod Identity. This is a non-Kubernetes specific way of setting the same thing up. So the reason that you might want to use this, there's pros and cons here. It doesn't require you to do all of that OpenID Connect configuration. So that's a bonus. If OIDC is confusing to you, or if you think, oh, that just sounds like a lot of identity work to set up, you can install a new add-on to your cluster for pod identity. So you go in and install this agent that runs on the cluster. And then you set up an IAM role that trusts the pods.eksamazon.com service. And that will allow you to create an association between a pod and a role in the AWS control plane, not inside of Kubernetes. So you don't really have to do anything inside of your Kubernetes manifest to set this up. So this is a way to simplify it, but it is AWS specific. So I would say, think this through a little bit. It depends on your requirements. If you know that you're going to need to set up workload identity inside of multiple clouds like Azure, AWS, and Google, this may not be the best path for you because this is a one-off and it doesn't really translate over into other Kubernetes services. So I'd argue it's still very important to understand how OpenID Connect works in the previous two demos that we looked at. The benefits of using this is that it is easier to audit the permissions for pods inside of the cluster, because rather than iterating over all of the different service accounts and seeing, do you have an IAM role mapping, you can just run one EKS command and list out all of the different roles in the pods that they're associated with. So pros and cons. I think it's important to understand OpenID Connect, but I'll show you how this is all set up as well. So the command, all you're going to do to set this up, so I've got a web pod actually running over in Sabre in the other namespace as well that we'll take a look at. In the Sabre pod, all I did was say, on my cluster, I would like to create a pod identity association. And I'm giving it, here's a role ARN and the namespace and the service account that's in that namespace that I want to give permissions to assume the role. And that's it. You run it, and it will create this pod identity association inside of the EKS cluster. When you do that, it injects two separate environment variables. So it creates an AWS container credentials full URI environment variable. That's going to be a local path, basically a miniature instance metadata service that you can run a git command against to pull temporary credentials down for that role. And then to access this credentials URI, you need to pass in an authorization header that contains the JSON web token for that pod. So the story here is that you are going to grab a temporary credential using a different JWT from the local service endpoint that's being managed by that pod identity add-on. And then you can just assume the role the same way. So in the last demo, let's take a quick look at this one. Oops, let me get back to, so we're still in the AWS setup. What I also want to do is, so I've got the deployment YAML. That's the one on the left here. This is the one that used workload identity federation. And then I've got a pod identity one. And I just wanted to compare what the differences were here. So you'll notice this compare on the right. This is the old pod or IRSA, the IAM roles for service accounts setup. You'll notice in pod identity, that annotation is gone. You don't need that anymore. And then the namespace is different. One's over in DM, one's over in Sabre. So really, we're just removing that annotation. Everything else is the same. So without the annotation, how does Kubernetes know which role we're going to assume? And that happens when you run that create pod identity association command. So after I've got the service account set up, if I go into EKS, let me show you that association here real quick. We're going to go into our cluster. And if you look at the access tab here, we'll go down, you can see the pod identity association there. So this is the equivalent of that custom annotation that I showed you. So here's the IAM role that we're going to associate with the Sabre Web SA service account. That configuration has to be there before you deploy the pod. So there's a timing thing here. You've got to, one, create the service account, two, create the association, and then three, deploy the pod for all of this to work. So let's now take a quick look at what's set up on the cluster. The add-on I mentioned, you can see that that's installed. If we grep all of the different pods in the cube system namespace, which is where a lot of the system services are running, you can see that we've got this EKS pod identity agent running. Now that agent is going to look for, if we go back over here, it's going to look for pods being deployed with the Sabre Web SA service account. And if it finds one of those pods being deployed, then it's going to inject those environment variables for you. So as we take a look at the projections here, you'll notice we do have a pod identity token that was injected. And if you take a look at the environment variables, we've got that credentials URI and also the path that contains that JSON web token. So following our pattern here, let's exec into the container, take a look at it. So we're now inside of the Sabre web pod, and we are going to grab the value of this token. So this one is going to be slightly different. So let's exit out here, and we'll say JWT equals the new token value, JWT decode, JWT, and you can see the audience is slightly different here. Notice it's not STS Amazon AWS.com anymore. It's not coming in through the AWS identity provider anymore. It is using pods EKS Amazon.com. And then the issuer and the subject are basically the same. So that audience is important because it's what's going to actually allow it, let me exec back into the container, it's what's going to allow it to communicate with that credentials URI. So if you remember, if I run env and then grep AWS underscore, notice we've got the URI here. So I'm going to make a request to 169.254.170.23 v1 credentials. And in the authorization header, I'm going to include the contents of that JWT. So this is going to make that request with the JWT and the authorization header to the URI. And locally, your command line interfaces, your SDKs will look for those two environment variables, run that command, and you're going to get your temporary access keys and your session token for talking to the AWS APIs. So the end result is the same as the IAM's roles for service accounts path. It's just a different way that we can assume that role using a built-in mechanism for EKS instead of the more general OpenID Connect path. All right. So let me exit out of this container. We'll do a quick conclusion here. So jumping over to the closing remarks, hopefully this crash course in the different ways pods can authenticate to the cloud provider APIs showed you that there's a lot of different ways you can do this. Some of them are better than others. Long-lived credentials, cross those off. Long-lived credentials must die, as we say. And another best practice there is to eliminate the permissions inherited by the nodes, role, or service account that we've attached to it. We should be disabling pod access to the instance metadata service in general. And that's going to allow you to force all of the pods to get their identity through either workload identity federation or something like pod identity. So as I built this thing out, I ran or created a couple of scripts that can help you audit these things. And the link is on the bottom of the slide to my GitHub repo and the gists that I've got there. So I'll show you real quick some of these scripts that we've been using. Let me show the bash RC extensions file where a lot of this stuff, there's a lot of things in here as well. But I wanted to show you that JWT, here's the two JWT decode shortcuts, Chad. I know you had asked about that earlier. So what I'll do is I'll add a gist with these in here just after we wrap up the webcast so you can take a look at them. So that's what the JWT decode looks like. You got one for the payload and one for the header as well. So I'll drop that into the gist. The other items that are in there is I've got an AWS, let's do the AZ one first. So user, local, bin, and AZ. So I wrote just a loop. Auditing which pods have which permissions can be challenging. So what I wanted to do is actually query from the Kubernetes control plane. So I'm going to search for all of the service accounts that have the workload identity client ID value set. And if we run that, we can go ahead and just iterate over all of the different Azure workloads and see, okay, here's a service account in Azure. Here's the service principal name that it's mapped to and the client ID. And then this script will actually iterate over any resource group role assignments that it has as well. And that's in the gists in the link that I just showed you to. And I'll go back to that slide in a moment. I've also got AWS scripts that'll EKS audit, and it'll do both ways. So if we go to those, we've got one for the IRSA pods. So we can run that one, and that's going to go through all of the different pods that are running inside of your cluster and say, here's the Kubernetes service account, here's the role that it's mapped to, and any policy attachments that it's got. So you can kind of get a big picture of which pods have which permissions. And then the final one is doing the new pod identity method, where it's going to, oh, I've got to give it a cluster name on that one. So DM app EKS cluster. So that does require an argument. And that'll go through and it says, oh yeah, you've got one more in the Sabre namespace. You've got web SA that's mapped to this role. And there's the policy attachment for that as well. So a couple of different audit scripts that are available in the gist link down there. And Chad, I'll get the JWT shortcuts in there as well, so you can kind of take those and run with them. Just be aware that does require certain tools to be installed in your shell, so you may have to kind of battle with that one a little bit to get the right dependencies there. So that wraps up the workload identity discussion. I know we covered a lot of ground in an hour. Hopefully, you had some fun stuff to take a look at and got a feel for workload identity. This is just one of the many different topics that we cover inside of the SANS cloud security curriculum. Check out the flight plan that's out there on our website at sans.org/cloud security. Lots of different ways that you can get involved with cloud security there. Closing remarks. This is one of the new topics that we have added into SANS Sec 540 cloud security and DevOps automation. We've got some runs upcoming. Actually, on Monday, a live online class starts with John Ziola, or if you're in the New Orleans area, feel free to jump down there. John's teaching the course again in Orlando in late March. And if you're up for making a trip out to Oslo, I will be in Oslo April 22nd to teach that course as well. So with that, if you've got questions, I think we're about out of time on the webinar. Feel free to jump out to the SANS Cloud Security Discord, and you can drop those in the there's a couple channels out there, but just ping me in either the I think there's a workshops channel or the Sec 540 channel, either one, and I can kind of answer your questions out there. With that, enjoy the rest of your day. Thank you so much for attending, and we will catch you next time around. Cheers.